see. All right. Get started. I'm excited about this lecture because we all use object-oriented programming languages, maybe some under duress, but it's kind of a really cool thing how you actually implement this stuff. So we talked about array indexing and array access a couple of lectures ago when we were pointing out this issue that C doesn't really prevent you from shooting yourself in the foot. In fact, if you want to shoot your foot or your head or your arm, you are free to do so. And I gave you this code where we had a 4-element array where the indexes are R0 through R3, and we can also access R4, and even weirder, we can also access R-1. C does nothing to prevent you from doing this. And depending on your variable placement, this could affect A or B or both. Probably not, because they'll probably be in registers. You could affect the caller's EBP, which means that you return, you think everything's fine, and actually you didn't blow away your foot, but you blew away the foot of the person standing next to you. Or you might jump into La La Land. So you have no idea what might happen. It may be also that you have no idea that this is a bug, because it doesn't affect anything, and you go merrily along not realizing that you're writing to stuff that you're not allowed to write to. And this actually is unfortunately all too common. I could tell you numerous stories from the software engineering world. I've been writing software for over 25 years now, and there are some horrifying things that go on in software that you probably are running right now. So enjoy. So anyway, one thing that we could do is add metadata to our arrays. And if you've been looking through the slides online, there were some slides about this earlier on, like 2 lectures ago, but I excluded them from the lecture itself just for the sake of time. But this is an interesting C technique that you can use that a lot of people aren't actually aware that you can do. Notice I have a struct, and the last element of the struct is this array, but then I say, I don't know how many elements are in the array. It turns out you're allowed to do this. What you do is you allocate a struct that is the size of the struct plus as many array elements as you want, and then you can use values to index those elements. So you would do something like this. Array underscore T star A, so we have a pointer to our array type. We malloc size of array T, so whatever that thing is. Anybody want to guess what size of array T would be? On a 32-bit platform, GCC? 4. That's a very good answer. It turns out that values is not really a thing that is represented in memory. It's represented by the compiler, but it's the starting address of everything after length, basically, is how it's done. So like I say here, A arrow length is N, and then we could say A arrow values 0. We could say array, or I should say A arrow values 1, and so forth, and it'll do the right thing. The compiler will present that abstraction to you. Okay, questions? Sometimes I like to use this kind of crazy thing on the midterm, so just be aware that it is possible. And if we have this kind of metadata, now presumably we could start making a language that sucks a little bit less. I shouldn't say that because there's a lot of C code out there that does some pretty powerful and profound things. But that at least is a little bit safer for programs to use. So like I have here, we can use a.length to iterate over the elements in A. We know how many elements there are. And hey, maybe we could even start making it more powerful. Like we'd like that length to be read-only. And we'd like indexing operations to be checked against that length so that if it's outside the bounds, we don't just blithely go on and do it. We actually say, you know what, your program has a bug, and I'm going to stop running it because your program needs to be fixed. It does incur a performance hit. And so there's some really interesting things. You're going to get me off track. So, but I'm going to talk about it anyway for like 30 seconds. There's a whole area of compiler work called data range analysis, where when you have code like this, you can look at this and say, well, I is allowed to range from 0 to length, and as long as your types all match up properly and everything, you can say that there is an invariant in that loop, that I is going to be within the appropriate range of that array. And so you could say, well, I as a compiler, since I'm analyzing this code to some limited amount, I can say, since I is always going to be in range, I don't need to perform array bounds checking in this loop. So you can imagine situations where you're like, well, this variable access or this indexing operation on an array is not necessarily guaranteed to be within bounds, so I will perform bounds checking, and yes, I will incur a tiny performance penalty, which honestly, slow and correct is much better than fast and horribly wrong. So it's always good. I mean, even better is fast and correct, but it's not always a guarantee that you'll have that. So anyway, but yeah, that's my aside. So if you want to study that kind of stuff in compiler research, go for it. It's awesome. And so like I say, if only our type could also expose specific behavior. So let's say that we want to start being able to perform operations on the values in our structs and so forth. And so this leads into the concept of object-oriented programming, where I have some related data values that are grouped together into a unit. I can operate on them through operations that unit of data provides. And now I've suddenly concocted the notion of an object. And when you have objects, then it's nice to have a description of what goes in them. Not every object-oriented language has that. And not every object-oriented language is as strict as other languages. So for example, in Python, when I create a class and say, these are the things in my class, when I instantiate that, I can add other stuff to it programmatically. I'm not constrained. In C++, I'm constrained. In Java, I'm constrained. I'm not allowed to add new members from outside the object, but you can in Python. Python's very flexible that way. I'll use the positive term flexible. Okay, but a class describes what appears within objects of that type. So we have a couple of object-oriented programming concepts, and these are pretty important to understand if you want to be a good object-oriented programmer, because these are things that motivate a lot of our decisions and considerations in architecture and design. So we have encapsulation. I don't want to allow direct access to members unless it really makes sense. If I have a card deck type, I don't want to allow people to get cards willy-nilly. I want to constrain, like you can only take the top card, or you can take the top n cards if you're drawing a hand, something like that. Okay, so I have accessors and mutators that control when and how state is modified. So that's encapsulation. That's defensive or inward focused, protective. And abstraction is more outward focused. I want to present a simplified interface. Again, card deck. I want to have a way of shuffling the card deck. I don't want the caller to have to think about, well, what algorithm is being used? Is it random enough? Blah, blah, blah. I just want them to be able to call one operation on this data type, and boom, I know that the card deck is now shuffled. Okay? And so like I hear, you can do composition as well. I don't find this example particularly compelling, so maybe I'll remove it next year. But car has an engine, transmission, and so we can imagine that this corresponds pretty well to real life. Maybe it would work better with a rocket ship because you would need to control stuff in a rocket ship. Although now, a lot of this stuff is actually controlled in a car with software, so maybe it is a good example. So the premise is that with things like encapsulation and abstraction, it must make it easier to create larger programs. And so like I say here, I can constrain state transitions. I can verify state all the way along, so presumably it'll be less likely that I write bugs in my programs. That's the whole idea behind object-oriented programming. And of course, that is something that is debatable, although there's plenty of experience now writing object-oriented programs. But there are people out there on the internet, if you want to go look for them, that are absolutely dead set against object-oriented programming. And it's good to read their arguments and think about what they have to say to see if there's anything there. Okay? So it certainly is something to consider. But there are a lot of different object-oriented. You can tell that these people are not in the majority because now pretty much everything has objects, some kind of object-oriented programming. They even added it to PHP. I don't know, maybe you didn't realize that it didn't have objects before, but it sure didn't. And Perl, same thing with Perl. They added objects to Perl. What? So anyway, we have all these languages now with object-oriented features. And so what we're going to do today is look at how we might implement some of the object-oriented facilities that the Java language has in C. If we were doing something crazy like trying to emulate these things in C. And we're going to do a really bad job, but we're going to do the best job that we can in the limited time that we have. And it'll illustrate how languages like C++ and Java work under the hood. So like I say here, Java has a specific object-oriented programming model. This is a very simple class here, representing red, green, and blue colors, yeah. And so we have some variables that we recognize. Now, the class itself is kind of a global variable, and so I'm going to use air quotes around it. That's why I use a dotted line here, because it's kind of a global variable. You'll see that it is a name that is globally recognized within our program. So we can refer to it that way. So I'm going to call it a global variable. We have function arguments, which we do understand pretty well, and local variables we also understand. We know how to do these things so far. We already saw an example. We know how to translate this into IA32 if we decided to go ahead and do that. The object-oriented model introduces two new kinds of things. At least Java's object model introduces two new things. We have class variables. So now we have variables that are not associated with the specific object, but are associated at the class level. So here we have a constant red. You see the red component is 1, the green and blue components are both 0. And then we also have instance variables, red, green, and blue. When I instantiate an RGB color object, it has its own copy of red, green, and blue. I create a new one. It has its own copy of red, green, and blue as well. Okay, so we have to find a way of representing these things. Now, since we kind of use this whole notion of environments or frames, we're going to try to figure out how to stitch these things together, and then how might we represent those things in C. That's the way we're going to tackle this. So this would be an example environment structure we could use. Again, I don't know how much Mike talks about the environment model in CS4. It used to be a huge thing in CS1 when CS4 was CS1 and CS1 Python didn't exist. Physicists had to learn scheme. That was our greatest coup. So anyway, but we have here an environment structure, the global environment. We have this RGB color name that we can use to refer to the RGB color class. In there you can see we have a class variable that refers to RGB color.red, so we call it red, and it's got the our object that just represents the red color. And then if we were to instantiate some other RGB color object, and notice that we can call this function from HSV, which is a different color space, hue, saturation, and value. Then we specify hue of 0.5, saturation of 1, value of 1. And in there, we have local variables. So you can imagine, again, frames stitched together to represent this sequence of operations being performed on a color. Okay? Any questions? This is the concept. This is what we're basically going to do. And you can see that it generally models this quite well. You do basically the same thing in Scheme, or now I guess you would use the term racket, if you were going to represent objects in Scheme, trapping frames and so forth. But we won't go into all of that with lambdas and blah, blah, blah. Okay, so here's our environment structure. What we're going to do is introduce a few new frames to represent these various new things. So we need some frame to represent the class, and we need another frame to represent objects. And then we'll just instantiate those frames anytime we need to be able to represent things. We can use the memory heap for that. This is definitely not going to go on the stack. It wouldn't make any sense to put it on the stack. And if we're really careful and start making our pointers more opaque and reduce the things that people are allowed to do with them, a la what Java does, where you're not allowed to add numbers to references and get new references to random things, or cast references to other kinds of references in weird ways. You're not allowed to do that. So if we do those things, then we can go ahead and provide precise garbage collection as well, which is really neat. And even further, which I mentioned here on the last point, Java has this really interesting thing where it can even garbage collect types, and that will allow you, for example, to do dynamic class loading so that you can start a class loader, run one version of your application, all your classes get loaded into that class loader, and when you're like, well, what I want to do now is actually hot upgrade my application, I instantiate a new class loader, load my new version of the application into that, and when all of the services that were in the old application stop and are no longer running, all of those things can be reclaimed. So it's a very powerful model. And that's what allows most of the Java server software that we use to actually run and be hot upgradable on the fly on a running system. There's some really neat stuff there. Okay, so like I say here, how do we implement this in C? And I already told you, I already gave you the caveat. We're going to do a very simple approach so that you can get an idea of how it works, but this is not a class on how you compile object-oriented languages, so we're not even going to go all of that great depth. But like I say, we will be able to build it up until we include most of the basic object-oriented programming concepts. Okay, So that's actually pretty neat. We're going to go through most of the stuff that you need to know for how C++, how Java actually do what they do. Okay. So we have this stuff, and since we already know how to implement some of these things, we're not going to talk about them because we're just going to like wave the magic wand and say stack, and those things will be implemented on the stack. So when we pass arguments, we pass them on the stack. Local variables can live on the stack, and that problem is solved. We're going to just rely on our existing solution to implement this part of things. But how would we store this object data? Any ideas? We just talked about something a couple days ago that we could use for this. A couple lectures ago, I should say. Remember, C has this notion of structs. We could use a struct to represent these various members. We can give struct member names. They can have different types. So that seems to match pretty closely to how we would represent an object. So we can do something like this. Notice we're translating this RGB color data. So now we have a struct, and it only has the data members. We don't have any operations or anything like that exposed on it. And like I say, this loosely corresponds to a class declaration. We could easily translate it. You may or may not be aware of this already, but early versions of C++ didn't have their own compiler. They actually translated the C++ code using mechanisms exactly like we're talking about today into C code, and then it would compile the C code using a C compiler. And that continued all the way up until we had exceptions, because exceptions fundamentally violate the way that C works with the stack. And so, well, we'll talk about that on Friday. But, you know, the C++ language was implemented in exactly this way for quite a while, which is kind of neat. So anyway, every object of RGB colors type that we might instantiate and use, we'll just create another instance of the RGB color data struct. We'll do that. Okay, now we need a way of providing methods. So notice we have getRed, setRed, and so forth. And there's no explicit argument representing the object. It's kind of implied because it's c.setRed. So it is a parameter, but it's an implicit parameter in the syntax that we have here. We don't have it, and what I mean by that is we don't have it between the parentheses. It's just a syntactic variation. Okay? And if you have worked with Python, then you already know the punchline to this part. We'll introduce this implicit parameter that we go ahead and pass to our operation so that the operation knows what object is actually being operated on. That's all we really need to do. So in Java, we have this. In C++, we have this. And that's just a reference or a pointer to the object that the method is called on. So if I have something like setRed, and inside the implementation I say, well, my red member is going to be set to whatever value v is passed in, then I just translate this into some C code that looks like this. RGB color underscore setRed, so we have some name mangling, which also occurs in C++. And I pass in an RGB color data struct, and I'll call it this. And then I also have my float v, and I say this arrow red equals v. Okay. Really simple translation. And this is exactly how object-oriented languages work. Okay, so yeah, that allows the object's code to refer to its own fields. So when a program calls a method on an object, the translated implementation, or if you're in Python, the interpretation of that is that we're going to pass the object as the first parameter, and then the remaining parameters come later, and that reference is used to access fields to call other methods. Okay? And this would be the Python version. So just in case you happen to have escaped somehow writing Python code at this point in your life, this is how we would do the same thing in Python. And you can see in Python we call it self. Init, that's the constructor of RGB color. Self, red, green, blue. And then self.red, self.green, self.blue, and so forth. Get red, you pass in self. So even though we don't have an argument to get red, the implicit parameter self is passed, and we return self.red. Okay? If we have other methods being called inside the object, again, we have to do something about this, because getRed also needs to know what object it's operating on, getGreen needs to know what object it's operating on, and so forth. So if we have a getGrayscale method that turns around and calls other methods, we do the same thing. We just translate it into RGB color underscore getRed this. We pass in the this that we receive to get grayscale, and we just propagate it along. Okay? Any questions about this? I realize this is incredibly straightforward. It is not going to be the most complicated part of the lecture, for sure. Okay, now once we have this, we know how to implement our objects. And like I say, our programs can manipulate independent objects of a class. So now I just instantiate different RGB color data objects or RGB color data structs, and then I can just pass them to the translated versions of my functions. So we can now see how to translate this into C, which if we know how to translate this into C, then we can implement this in assembly language as well. So we know we can run it on our machine. The last thing that we need to figure out is this class level constant. Notice we have this public static RGB color red. This is, again, a common feature in most object-oriented languages. C++ has static, Java has static. Java relies on static heavily because everything in Java has to live within a class. So when people want a top-level function that's not associated with objects, they have to make it static. If they want some constant that's not, a top-level constant, kind of like a global variable or a global constant, they have to use static to declare it. So here we have public static RGB color red. And I see here we don't access that member through a specific object. Instead, we just use the class name, so rgbcolor.red. This is why we kind of think of it as a global variable in our sort of abstraction that we're creating here. rgbcolor.red. And so we need some way of storing red as well. So we'll have a frame at the class level as well. And we will also introduce the constraint or the notion that object frames should be able to reference their class frame. It helps us to have a couple of big benefits. One is, if you're familiar at all with Java, you can basically ask any object what its type is and get its class information. In fact, on Java Lang object is this method called getClass. And it returns another object representing the class. We can implement that very easily if we have our object structs have a pointer to their corresponding class struct. Okay? There's various other benefits as well. So there seems to be good reason to go ahead and have the object frames reference their classes frame. So again, simple translation, RGB color underscore class. And in there we have one member, which is a static member, like I say here, RGB color underscore data red. So this is going to represent our red color. And our RGB color data definition changes because we want to be able to store a pointer to our class information. You can see that, again, we have this interesting thing that there's a circular reference between classes and objects. So now classes have an RGB color data star for members that, and this is really only if you have a constant of the same type. And then the data object also has a pointer to the class type. So you have to jump through a very small number of hoops to do this in C. It turns out to be extremely straightforward. You'll see on assignment 4, I give you an example of this. So the question now is, how do we initialize these static members? Okay. We really haven't talked about that, but what we can do is start introducing the notion of instantiation time operations. Okay. We already would have that for RGB color. We probably need a constructor that can take red, green, and blue values and store them into the members. We kind of glossed over that. We won't in a moment. But similarly, we can do something like when the class is accessed for the first time, then I'll go ahead and initialize the class's information. Things like static members. Again, this is exactly how Java works. The first time your program runs code that references a particular type, the virtual machine goes and loads that type, and if the type has any static initialization to perform, that is when it's performed. So we can basically pretend that something like that is happening as well. Okay, because again, remember, this is just a sketch of how this all hangs together. Okay, so here would be the thing for initializing a class. And notice we have RGB color class init. We pass in the RGB color class star because this is the class that we're initializing. We set its red member to be a new object of the RGB color type. So we malloc some chunk of memory that's the size of RGB color data, and then we call it a init thing. Okay. Now, I want to point out here an interesting little side note, which is very important to understand. in many object-oriented languages, instantiating an object has two steps, and you should understand that there are two steps occurring. The first step is getting a chunk of memory that's the size of the object. And that's nice, but you don't have an object yet. You have a chunk of memory with who knows what garbage in it from whatever was occupying that memory before. So the second step is to actually call a constructor on that chunk of memory so that you can set all the members to be the appropriate values and so forth. Okay? So make sure that you understand that there's two steps. This is definitely hidden in languages like Python and Java. It's not so much hidden in C++. For example, we have the new operator, but you also have another version of new called placement new, where you can hand it a chunk of memory and say, I already took care of finding some memory for you. Why don't you just call the constructor on this chunk of memory for me? And so that's what placement new does in C++. But same thing with uninitialization or destruction. We have two steps. We have to call the destructor or the finalizer or whatever we have for our particular. Like Java doesn't have destructors, it has finalizers. And then we have to deallocate the chunk of memory as well to say, hey, this memory is now available for other things. So this would be the RGB color constructor. Okay, so notice we have red, green, and blue components. Those would be the actual arguments to the constructor that we would specify in Java. In our translation, we have a couple of other things we have to specify. Well, what's the class for this? And what is the actual instance for this? Or what's the chunk of memory that's going to be used for this object? So then we just initialize everything. This arrow class is the class, this arrow red is red, and so forth. Okay, we just go ahead and set all those things up. Any questions? You see now we actually have incorporated our ability to do these static members as well now. Really, really straightforward. Okay? So if you have all of that, you feel pretty confident with all of that, then that's awesome. We can go on and start talking about the next thing, which is this crazy concept called polymorphism, which I think is crazy intuitive. And the way C++ does it, for example, is not incredibly intuitive. But let me just sort of illustrate to you what we mean by polymorphism. We have a notion of class hierarchies now. We have some generalized base type, and then we create specializations of it. And so the specializations may have slightly different behaviors for common operations. They may have slightly different fields in them, because I need different data to represent things. In the C++ track, we talk about if you were going to implement a real-time strategy game, which is one of my favorite kinds of games since I'm terrible at first-person shooters, or any of these like turn-based strategy games. We wasted many hours as undergrads playing those games in our dorms because the internet just became a thing, and we were excited because we could waste time playing games on the internet. So anyway, I mean, the internet was around for a long time, but you know, we didn't have Ethernet in our rooms. We actually had to run cables through hyperspace to hook everybody's computers up, so it was kind of an effort. But anyway, that aside, you can imagine like some kind of abstract game unit type, and then from that you have armies and tanks and trebuchets and horses or whatever you want. And all of these things have perhaps different kinds of information they need to track, but also have different behaviors. And so we'd like to have some generic type that represents all of these specialized types, but the specializations provide different functionality and so forth. So polymorphism is this notion that if I have this hierarchy of types, then I can write code that uses pointers or references to the parent type, and when I call the various common operations, the operation provided by the subtype is the one that will be used, based on what kind of object I'm actually referencing. So that's the notion of polymorphism. You know, poly means multiple, and morph, you know, is like a shape or form. So it's like many forms. It has different behaviors based on the types of the objects that are actually being utilized. So what we'll do is we'll extend our example a little bit. Instead of having RGB color, which is one kind of color space, if you're familiar with color spaces, we'll have a couple of different color spaces. And we'll create a generalized color object, or a color type. And notice we'll have common operations, 2RGB, and get grayscale. And 2RGB will basically just give us a version of the color we can use in hardware. Okay, so 2RGB will pack the color up so that we have values 0 to 255 for red, 0 to 255 for green, 0 to 255 for blue. This is a very common way that graphics hardware receives colors and then manipulates them. Okay? The top byte is often used for alpha blending so that you can have transparency or translucency as well. And then we have get grayscale, which takes that color and just turns it into a black or white grayscale value. Okay, and then we'll have two subclasses of this. We'll have RGB color, which we already understand, red, green, and blue. And we'll have another one, HSV color, using the HSV color space, which, like I say here, effectively implements a color wheel. And a lot of times, if you happen to be, a more artistically inclined person and like using, probably Photoshop would be a good example, or Illustrator, or any of these graphics drawing programs, you've probably come across a color wheel at some point. I mean, even PowerPoint has a color wheel if you want to change the color of an object. Okay, color spaces. So these are color spaces, ways of representing colors. So RGB mixes red, green, and blue components. And so it's oftentimes indicated by a color cube. And you can see that if we have maximal red, green, and blue, we have white. If we had no red, no green, and no blue, we'd be on the opposite corner of this cube, which we can't see right now because it's at the back, but it would be black. And bottom left, we have no blue, no green, all red. So we have a red corner, a blue corner, and so forth. And so you can see that by mixing these colors, we get various other colors. And so you can represent quite a lot of colors that way. HSV is similar, except that the hue, actually you'll notice, is an angular component. It represents, like I said, a color wheel. So 0 would be red. Guess what color 1 is? Also red, because you go all the way through red, orange, yellow, green, blue, purple. And then as you start removing the blue from the purple, you get back to red. And like I say here, it is very intuitive for human beings to select colors using HSV. It also turns out to be really great for computer vision because you can basically represent the color of things with a single value instead of 3 values. And so if you're training a neural network or some other kind of learning system, you have one color input that you can use. Okay? So this is why we like HSV. There's many other color spaces as well, but these are two of the most common ones. So we will do something like this. And you can see that now we can start creating other methods that use our generic base type. So shape.setColor. I don't care how you want to represent the color. I just want a color. Graphics.setColor. I need to display a particular color. I don't care how you represent it as long as you implement 2RGB correctly. Okay. Yeah, and programs can use the version of color that makes sense to them. So we might have, for example, something like this. Notice in our graphics class we have a setColor method, just like I have up there. We call setColor. And inside here, we say to the hardware, hey, I'm about to draw, so set the RGB color to be whatever this color says its RGB value is. Okay? And you'll notice if I pass in an RGB color object, I want it to call the RGB color version of 2RGB. If I pass in HSV color, I want it to call the HSV color version. So this is an example of polymorphic code. Depending on the type of the object I pass in, it'll call the appropriate version of 2RGB. Okay? Polymorphism is a fancy name for a simple concept. All right? Make sense? Okie dokie. So let's see how this would work. Yeah, so this is what I was saying. They provide different versions of this function. So basically, we need to call the appropriate version of this function based on the type of the argument. And you can probably tell from this that if we need to have this set color code call the right version of 2RGB, then the object we pass in somehow needs to know which version is right for it. So if we pass in an HSV color object, it knows I need to use my version of 2RGB and so forth. Okay, we need to find a way of encapsulating that. And that introduces the notion of virtual functions. Again, this is something that is explicit in C++, and in Java, everything is, well, I shouldn't say everything, but virtually every instance method is virtual. Okay. So yeah, subclasses have their own implementation, so code written against the base class should call the appropriate version when passed a subclass object. Okay, so that's what we mean when we say virtual functions. So since objects already have a reference to their classes, this suggests a very straightforward solution to this problem. What we can do is when we instantiate our classes and we initialize the members of our classes, our static members, why don't we also set up some kind of table or structure where we can say, hey, this class's version of 2RGB is this function, and a different class's version of 2RGB would be this other function. And then, like I say here, we can use the class's information to figure out which version of the function to call. So C has function pointers, which are all the excitement of regular pointers, plus you can use them to invoke code, so you can really jack up your programs. But like I say here, instead of pointing to data, it actually points to a function. This is the way that you would declare it in C. So notice FP is the actual name, but it's nestled in between a bunch of other syntax. And what we're saying here is that FP is a pointer to a function that takes a double as an argument and returns a double. You can set these function pointers to point to functions by just referring to the function by name without actually invoking it. So we don't have parentheses on the sign call. We don't have any argument. We just say sign. I want my function pointer to point to sign. So if I want to invoke it through the function pointer, I just use the function pointer as if it were a function. Notice fpx. Okay? So that's the basic concept of function pointers. This is a very powerful concept. Lab 4 contains a scheme interpreter, which I wrote from scratch. And if you're curious about how to do that kind of thing, you can go in and look at how lambdas are represented so that you can have lambdas that are implemented in C code, you can have lambdas that are implemented in scheme, and so forth. And function pointers are a fundamental aspect of how that all works. Okay, so this is our base class representation. Notice now that we've added a couple of function pointers. We've kind of gotten rid of our other static member, like what is red. We kind of don't care about that anymore. So we're just going to focus on how to do this function invocation polymorphism stuff. And you'll notice that we have two pointers, 2RGB and get grayscale. 2RGB doesn't have any arguments, so we just pass in the implicit parameter. And get grayscale also doesn't have any other arguments, so we just pass in the implicit parameter. The subclass type information is going to be the same. Okay? Notice RGB color class. It's a subclass of color class. We still need to have these members. You'll notice that the arguments are slightly different. But think about this from the standpoint of the C compiler or the assembler. Because the C compiler is going to look at this and it's going to say, all right, I've got a struct called color class and it's got two members and they're both pointers. Okay, 4 bytes, I'm done. Same thing with RGB color. Okay, I've got two function pointers, 4 bytes, I'm done. Okay? It doesn't care that the arguments are slightly different, and this is partly why we like C for implementing some of these low-level things, because it's more relaxed about converting between types. Like you could probably never do something like this in Haskell, probably nor would you want to if you're doing this stuff in Haskell. Okay, let's see, class inheritance with C struct. So this is the base type, notice color data. Now at this point, I don't know if we're going to have color be an abstract class or not be an abstract class. I kind of don't care. We're not talking about abstract types right now because that would probably be too much for the lecture. But we do have some base type that has a pointer to the class. That's all it really has. The subtypes will have more members because we know RGB color needs red, green, and blue. HSV color needs hue, saturation, and value. So we still need a class pointer. We have to put it first because that's the same member that our base type has. Okay? Like I said, we have to have the same type of members at the start. This actually allows us to rely on a clever-ish C trick that you can use, where basically if you have a number of structs, where one is sort of like a base struct or a parent struct, and you have subtype structs, you're actually allowed to work with these things as long as the structs have the same prefix. So they all have the same members at the start. Then you can cast back and forth between them, and you can still access the base struct type members. Okay, so like I said, you can cast a base type pointer to a subtype pointer, and the common members are going to be at the same offsets. So I have a color data star, I can cast it to an RGB color data star, presuming I'm actually working with an RGB color object, and the class member will still be the right value because they happen to be at the same offset and they're the same size. Okay. Any questions about this? That's probably one of the most subtle parts of this lecture, that you can do this. Again, this is relied on pretty heavily in larger scale C projects. Like Postgres, the database server is written in C, and it relies on this heavily because it has a type hierarchy for plan nodes and so forth, and it uses this technique. Okay, here's our class initialization code. So RGB color class init. We take a RGB color class star. What do? Well, we initialize our function pointers to be our version of the functions. So we set 2RGB to point to our version of 2RGB, and get grayscale to our version of get grayscale. Okay, very straightforward. Same thing with HSV color. We have to say, okay, I need the HSV color versions of these functions. And then it becomes really easy when we have a color star or a color reference to invoke the appropriate version. Okay? Because we can just look up the class and look up the appropriate version of 2RGB. Okay, let me see what I have here. So this is the RGB color data definition, HSV color data definition. So we still have the class pointer at the top, and then we have our own special members. Okay, so that's how each object knows which version of its methods it uses. So we had this code before. Set color, and we pass in some color. We don't know what kind of color. And all we do in there is we say device.setRGB c.2RGB. Okay? We would translate it into this C code. Notice what we have here on the right part of this statement. We have a color data. Well, I don't know what kind of color it is, but I know it has a class member, so I say C arrow class, and I know the class says what version of 2RGB to use for this object, so I just call 2RGB on it. And if I pass in an RGB color, it calls the right version. If I pass in an HSV color, it calls the right version. Okay? Any questions? This is basically exactly how virtual functions work, virtual methods. There's also two different calling patterns here that I want to point out. This would not be the case in Java, but it would be the case in C++. So I have to admit that I am sort of bending what we're using in our example. If this was all in Java, then we'd have the same calling convention on device as we do on color. But here we have an example of a non-virtual method invocation. Notice it does not look up on the device object which version of setRGB it should call. So this is called a non-virtual method invocation or a static dispatch, because we actually use the method that we determine from the compile time type of that variable. Okay. So I wanted to make sure to point this out because, again, in C++, you have these two distinctions. You have static dispatch and you have dynamic dispatch or runtime dispatch. You have non-virtual methods and you have virtual methods. This is what happens in non-virtual methods. The compiler picks the version of the function to invoke, and that's just the one it always uses. So you can see why this is fast. We don't ask anybody what we should do. We just do it. And so, of course, it's going to be faster. Virtual methods, on the other hand, we have a lookup. And so you can see that it's actually going to be a little bit slower. Okay? Like I say, the method is determined at runtime from the object itself. So like I said before, it's called dynamic dispatch or runtime dispatch because we use the runtime type of the object to figure out which version of the method to call. Okay? And it is slightly slower. Do we care? Not really anymore, because now we measure our system performance in gigahertz and all kinds of crazy high performance ways. Back when I was a frosh and the lab was still in Jorgensen, we actually cared about this because computers were really slow. Our computers would run on the order of 1s to 10s of megahertz, and there were no superscalar processors or anything like that. Caching was much more limited. I mean, it obviously existed, but it was much more limited. So given that was the case, we actually paid a lot of attention to when things were virtual or non-virtual. Now we have crazy languages like Java where it's like, oh, I'll just make everything virtual because it makes more sense. It's like, great, it's slower, but nobody cares because everything is faster across the board. Any questions about this at all? So I just want to make sure that you are aware of these things. So now we actually are able to do simple class hierarchies. There's so much we haven't talked about. We haven't talked about multiple inheritance. We won't. Don't ever use it unless you know exactly what you're doing. Do a lot of research because there are ways that you can end up in strange places. You'll think you're doing drugs when you try to understand what your code is doing. I mean, you could imagine you have a subtype, you cast it up to the base type, you cast it back down to the subtype, and you end up with a different pointer than the first pointer you started with. Totally possible in C++. So anyway, we won't go there. But anyway, our simple example, you can see that it's all pretty straightforward to implement in C. In fact, it's kind of tedious. The biggest complaint that we get on assignment 4 for the class inheritance part of it is, wow, this is tedious to go through and translate all this code. And yeah, it is. Maybe I shouldn't have made class hierarchy with 3 subtypes, but I did, so sorry. Anyway, you could always write the translator as a program, and then you get extra credit. So anyway, but yeah, this is very straightforward conceptually to implement in C. We have these structs to represent various instances and class information and so forth. We have virtual functions using function pointers. We just represent what functions go with each type on the class information, and it becomes very straightforward to look them up from the object itself when we're invoking a virtual method. So pretty nifty stuff. This is all, like I said, exactly how C++ and Java work. Now, that is all the, yay, look at what we did part of the summary, but I do want to point out that there are a few caveats and details that we need to specify here. One is, as I already mentioned, that most of the methods in Java are actually virtual. Okay? So you never have the non-virtual or the static dispatch invocation, or almost never do you have it in Java. Okay? That's just, it's not really part of the language. It was designed to be more intuitive than C++. Second thing, a lot of object-oriented languages have this thing called a virtual function pointer table, or vtable. If you do C++ programming and you work a lot and read a lot of lower-level books about how C++ works, or especially if you're doing Microsoft systems programming, you'll run into this vtable concept all over the place. Well, what that is that the compiler doesn't do something this sophisticated. There's no point to it. It just maintains an array of function pointers. So just an array of addresses. And when it's compiling the code, it certainly keeps this type information around in memory. But remember, it's just generating assembly code. Assembly doesn't care how many arguments the pointer needs, or is it a pointer to data, or is it a pointer to a function. You just generate the code to do the thing that needs to be done. Okay? So a lot of times, compilers will just assign functions to slots, and then it will refer to them by slot numbers, and then just generate the code appropriately. So you might see indexing into the vtable in the assembly code generated from C++ code to look up the appropriate function, especially if you have a large number of virtual methods. Okay. And yeah, Java is an interesting variation in that it actually refers to functions by name. Does anybody know why Java refers to functions by name? As opposed to C++, which refers to them by number. Since we have a little bit of time, I'll talk about this. There's this really interesting thing about binary compatibility in C++. Maybe you've heard people talk about, well, when I compiled the new version of this library, it broke backward binary compatibility. And part of that is referencing the notion that, well, when you call these things, you look them up by index. And so if you have a new version of the code and you added more virtual functions, the old virtual function should still be at the same indexes so that code that depended on those things being at that index wouldn't now call some different function than the one that they meant to call. Okay? So you have situations like that. Java is a very dynamic language where they expect you're going to have jar files. You may upgrade jar files. You may upgrade them in place so you have one part of the system that doesn't change and another part that does change. Well, you can't refer to things by slot index if you have things changing that way. You have to refer to them by name. The location of the name may change over time, so you have to make sure to save the name and use the name to look up the method to invoke. Again, we add indirection to the system so that we can make it more powerful. Okay, I just wanted to mention that. That's why that's there. Last thing, our example is so hard-coded it's not even funny. Okay? And it really, like, again, if you're really familiar with Java and you're familiar with things like Java lang reflect, so powerful. You can hand me an object and I'll tell you what type it is, what constructors it has, what methods and what fields it has. I'll be able to invoke methods. And having never seen that type before, I'm allowed to do that all in Java because of this very powerful way that it represents classes. So like I say here, we have very sophisticated data structures in Java to do all that kind of stuff. C++ doesn't have that. Neither does our example. We don't have anything like that. You can imagine how you could extend this to add that, but we certainly don't have that at all. Okay. So yeah, and it's this crazy thing that you can do, like say, you can even generate new classes on the fly and then load and run them. And there's all kinds of tools and utilities that allow you to do this. And a lot of application servers, when you hand them applications to run, they'll figure out how to interface with the objects, generate code to do it, and then load that into the application so that they can now have highly optimized mechanisms for interacting with objects. It's very cool. It's very powerful stuff. A lot harder to do in a native language because you have to generate machine code and then hope you got it right and then not crash. Okay? Any questions? Okie dokie, that's actually all we're going to talk about today. So we will see you all on Friday. Oops.